Welcome everybody. Thank you for joining our blockchains and smart contracts security workshop. This is a series of workshop we are hosting for post-COVID hack. And it's the third workshop from Laurence and his team from XtraP. Just want to say, first of all, thank you to all our partners. And also want to go through a couple of housekeeping rules. This workshop is recorded and we will share the slides as well as the recording in a few days' time. And also, regarding posting questions, please do use the chat feature on Zoom, and we will attempt to answer as many questions as we can towards the end when we have a Q&A session. Today is all around how to develop secure smart contracts. And Laurence will give you a brief overview on what he will cover throughout the session. Thank you very much. Over to you, Laurence.
Thanks, Antonio. Thank you to everybody who's joined. I hope you're all having a really good hackathon. And thank you to the partners and to Antonio for inviting me to do this workshop. I really enjoy, we've really enjoyed doing the workshop so far. So we're going to be talking this week about security. It's perhaps something that you may not think about as much during a hackathon, but I think it's really essential that you get a good mindset around security when you're developing on the blockchain. So I'm going to go through a little bit of theory to begin with about blockchain security, then we'll have just a quick overview, a reminder about what smart contracts look like and some of the different parts of those. Then we'll go into more details about how to protect your contract from malicious actors and what good practices are. We'll just cover a couple of the useful tools you can use to help you ensure that your contracts are secure. And then we'll go through some examples of when contracts have been exploited or vulnerabilities have been exploited, where things have gone wrong, and this has often been quite dramatic. And so we'll go through some of the more famous ones of those. I also have just a few examples of some vulnerabilities in contracts for you to have a look at. So if you go to that link, there you'll see some little snippets of code. If you want to have a look at those while I'm giving the rest of the presentation and see if you can spot what the vulnerability is or how you could exploit that contract or create problems, you can do that while I'm talking through the rest of this. But if you don't want to, that's fine. I'll cover them. I'll go through them all at the end and explain what the vulnerabilities are in those. Okay, so if we just start a little bit of theory around blockchain and security and think about, well, a good question to start with is with why would people attack cryptographic systems, cryptocurrencies, etc. And one of the main reasons, as you can see from this slide and a couple of tweets here for some really well-established people in the area, points out the amount of the amount of money that is involved, that can be involved, and these tweets are fairly old now. I mean, this is from both of them from 2016. But at that point, you had a third of the Bitcoin exchanges being hacked, which is remarkably high. Now, it's important, and we'll make this distinction when we look at the theory a little more. It's important to understand the different layers of attacks, and so this is not saying that Bitcoin itself is unsafe. It's that these are Bitcoin exchanges, so they're often using traditional technology. But this is to illustrate that this is a very lucrative area for people who may want to attack it. And part of this is also the fact that there is a pseudo-anonymity often involved with cryptocurrencies, for example. So people see it as a way, if they can steal some cryptocurrency, they feel they can get away with it. And they often think they will not get found out. That's not entirely true. And because of the way that particularly exchanges work, where they expect a KYC procedure, you may not be as anonymous as you like to think on the network, and you may have difficulty if you steal some cryptocurrency, you may have difficulty exchanging that back to a fiat currency if that is what you're wanting to do. But there have been some very large heists, as they're called in this tweet. Mt. Gox was a very early one. A huge amount of fiat equivalents stolen there. I mean, at the time it was a lot less, but certainly when Bitcoin is at its height, that represents a massive amount of money that was stolen. So that's one of the main reasons, people are going to attack or try to attack maybe your systems, is that they think there's going to be some monetary reward. Also, there is the fact, of course, that they may do this for fun. They do it as maybe as a technical challenge, or maybe it's a competitor of yours who will do it to try to destroy your system, to get rid of the competition. So there are plenty of reasons why people would want to attack your contracts, for example. And it's useful to look at attacks at different levels. You can think of the ones I've got here, the protocol level, the application level, and an economic level, ones that I find useful. So I'm not going to say anything really about the economic level, but this would be the case where perhaps if you've created a cryptocurrency, or maybe some DeFi product, this may be someone would use, perhaps they have a large amount of cryptocurrency that they can then use to attack yours by maybe buying a lot of your tokens and then suddenly dumping them, this kind of thing. So there are various economic attacks that people can make against systems. Also from the people who have written the systems, there may be scams where people get you to invest in a particular product with the expectation this product will last a long time, but then the developers do something called a rug pull. They do something to either disappear with all of the funds, or maybe they dump all of their funds on an exchange and make the price of the token drop, and so you'll lose out from that. So that's something at the economic level. The protocol level is where we're talking about attacks against the Bitcoin network itself, the Bitcoin consensus mechanism, the Ethereum or RSK consensus mechanisms or networks themselves. So these are attacks that, if you're writing smart contracts, you can't really do much about that. You have to hope that there are not vulnerabilities in the protocol layer, but you still do need to be aware of them in case that these things happen. And I'll go through a couple of those very briefly. And then what we will really concentrate on today is the application level. So this is really no different from the idea of bugs in any traditional application. When you're writing your smart contract, you may have the code may be doing something different to what you intended to do, and there may be that may be unknown to you for a while, and malicious people may come in and exploit that to their own ends. But let's have a quick look at just some examples of attacks at the protocol level. So one you will hear about on blockchains that are doing proof of work, consensus particularly, is the 51% attack. And this leads, an example here, leads to a double spend. So the idea behind this is that somebody has, by whatever means, amassed enough hashing power that they effectively have 51% or more of the hashing power of the network. And this would allow them to produce blocks at a faster rate than the other people, well, the people we assume are non-malicious on the network. And so a particular attack might carry on, as you can see here with these blocks, where we start with the blue block 20, and then honest miners are adding blocks 21, 22, and 23 to the blockchain. And in one of these blocks, in block 22, we have a spend of here it's 100 Ethereum Classic tokens. So somebody has spent 100 tokens and they've used this to get something valuable in the real world. So maybe they've cashed out their tokens and got some fiat in exchange. And then someone else has put in the next block 23, and this is honest. And then while this has been happening, the malicious person has come in and after block 20, they started mining their own blocks, but they haven't submitted these to the network. They've kept them to themselves. But they've done effectively in block 22, they've done a double spend. So they've, in addition to the 100 tokens that have been spent in one transaction, they've spent those in another transaction, which effectively has the effect of cancelling out this original transaction. And so if they've mined these blocks, they've got these blocks up to 25, they can dump these onto the blockchain network. And because we are following the longest chain, all the nodes will then switch over to following the red blocks. They will invalidate this transaction that has been used to, for example, get some fiat currency, and instead have the other 100 ETC spent. Maybe that was sent to another account owned by the attacker or one of their friends. And so at the end, by block 25, we have the situation where the malicious attacker will have received the fiat currency, but the exchange that is expecting to have the 100 tokens will no longer have these because that transaction effectively never happened. And so this is how a 51% attack can lead to a double spend. And the reason we've put Ethereum Classic tokens here is that this has happened a number of times now with Ethereum Classic. Happened well over a year ago initially, and then it has happened a couple of times in the last couple of months. Something similar, but perhaps less dramatic, and is something called selfish mining. The idea behind this is that the attacker here is the one producing the red blocks, and what they do is they effectively produce one block, but rather than put that out to the system, they allow the blockchain to continue until they have another block, and then maybe they will put both blocks out, and so they can overtake the system that way. And they do this to gain an advantage and to do this so that they can produce blocks more quickly than other people, because they will know if they've produced the first block quite quickly, then they can start on the second block and so start to produce a longer chain themselves. This is more of a theoretical problem, and so it's not as obvious how that when this happens, although it does require less hashing power than say the 51% attack. Network attacks, you can get the idea of eclipse attacks, where people try by some means, it may be by introducing malicious software to a node, but they can try to take one node away from the network so that node is no longer receiving transactions from the real honest blockchain, but is perhaps receiving transactions or malicious blocks from malicious nodes that are still attached to it, but are trying to convince this particular node, which may be a point of sale node. So somebody is in a shop is using this and this node to attach to the blockchain to record their transactions and to check balances. And so the malicious people are trying to isolate that node from the network and give it a false view of what is happening in the real network. Okay, so that's some of the things you may see just generally around blockchain, but at the protocol level. We're more concerned with what will happen with your smart contracts. So just a quick reminder about smart contracts. Yeah, they're not really smart. They're not really contracts in the traditional or any legal sense, and they're not too smart either. They're just applications that we specified on the blockchain. They run in an EVM. So, for example, the Ethereum EVM or the RSK EVM. The code is immutable, which has disadvantages and advantages. So, from the advantages are that once your contract has been deployed, you can be certain that no hacker is going to go in and change that code. The drawback, one drawback is that once you've deployed your code, if there's a bug, you cannot go and fix that in that particular instance of the contract. So upgrading is more difficult. So you really do have to be sure when you deploy your contract that it does exactly what you want, that there are no bugs, that the features are exactly what you want. It's perhaps a similar mindset maybe to where software is built for spacecraft, and once it's gone into space, it's very difficult to update. You should take a similar approach perhaps when you're developing your contracts and deploying your contracts. The contracts run in a constrained environment. We mentioned this last week, the week before. For security reasons, the virtual machine restricts what your contract can do. For example, we have the notion of gas on Ethereum to prevent people doing denial of service attacks using your contract. We also have we limit what the contract can see. So we do not allow to look at the operating system. We do not allow to make calls to the outside network. And the thing to keep reminding yourself is that by default, your contract and the functions in your contract are open to anyone. So if you write a contract and you don't do anything else, then effectively anyone who joins the network can call the functions in your contract and can interact with your contract. And that is probably not what you want. There may be parts of your contract where that's fine, but there may well be parts of your contract where you want to restrict who is allowed to do certain functions. And a lot of the vulnerabilities we will see, the majority of them really that have happened in the crypto space, have been caused by badly written or badly designed contracts, rather than a problem with, say, the Ethereum virtual machine itself. Okay, so we'll just quickly remind you again what the parts of a contract are. Here we have just a very simple contract that we showed this in the first workshop. So we have the version of our solidity specified at the top. Then we have a contract name, some variables, an event, a modifier, and a couple of functions. So from a security point of view, some things you need to think about. So the way this is written, if these variables, you can put some keywords in here. So you could put in between the uint256 and score, you can put in the public keyword. And what this effectively does is to write a getter for the score. If you don't do that, then you will have to specify how people get the score from your contract. Now, this doesn't mean, and also if you call this score, this variable private, this doesn't mean that this information is private in any way. Any information within your contract can be seen by someone who is determined enough to see that information. You may make it more or less difficult, but any information that you have in your contract, you should assume will be able to be seen by anyone out there. So if you have anything that's private or that you don't want people to see, then you'll have to take some extra care about that. Maybe you'll have to encrypt it before you put it into your contract. Okay, so that's some variables. We have one of the main means we have of restricting access to functions is by use of modifiers. I'll go over those more in a second. And then the way that people interact with your contract are via the functions. And we have a number of keywords that we can apply to the functions, and it is well worth being very clear about these. And I think it's very useful to be very clear about how you assign access to these functions, and have make sure that this is what you really intended. So the keywords we have, you can see here. So we have a view function here. So a view function means that we cannot use this function to change the state of the contract. We can only use it to read data from the contract. We've declared this as public, so this means that this can be seen, this function can be called from anywhere. It can be called from within the contract, it can be called from externally to the contract. I think it is useful to be when you're choosing the public or external or internal or private keywords to modify your functions, be as restrictive as you possibly can to begin with. If you have to be more permissive later on, then change it, but try and limit it as much as possible, just to make sure that you're not introducing any vulnerabilities that way. There is also the fact that there is a slight optimization if you have call it a function external rather than public. It does optimize the code slightly, but generally it's also better for readability. I think if you declare which functions are external, which ones are internal, then it gives you a better idea of the flow of the logic within your contract. Okay. So let's talk about modifiers. So they're the main tool that you will have in your contract for restricting who can call a particular function in your contract and how you can restrict access to a function. So I've spelt it out here. They are often written in a slightly easier way than this. But here we have the modifier keyword and then the name of the modifier. Obviously the name should give some semantic information about what it actually does. And then we have some type of if statement. And as I said in the first workshop, the way to think about modifiers is to think of them as wrappers around a function. And you can think of the function going in where you see the underscore here. And so this one is saying if the message sender, so the person who is calling this function, is the same, if the address there is the same as the owner, then we're going to carry on and run the function. Otherwise, we just drop out. What you will see more often than this is a require. So people might put require message sender equals owner. A require is just means that if it's the require fail, if the test fails, then it reverts. So you throw an exception effectively. It has pretty much, well, the effect is kind of the same. You would get an exception thrown there, whereas here you don't get anything, you just drop out. But in either case, you wouldn't call the function. Of course, there is a balance here to be had between restricting your functions so that you're preventing the wrong people from accessing your functions or doing any type of malicious behavior, and ensuring that the functions can be called by people who are doing legitimate behavior. So if you, by mistake, make these things too restrictive, you could effectively lock people out of legitimate calls to your functions. You could, also effectively create a denial of service attack against your contract if you make things too restrictive here. So do be careful about that and look out for that problem. Also, if you have special addresses in your contract, so here we have a special address owner, and we're saying that this address has certain rights within the contract, so we're going to give them access to particular functions, and that is fine. That is a good thing to do, but that then gives you the responsibility of making sure that you keep the key for that owner safe. So if you lose that key, then you will lose the ability to do those special functions, and maybe that will mean you won't be able to, your system won't run correctly. So if you have special addresses, do be careful that you keep them. Just to answer the question there, I think I kind of answered it anyway, but yeah, the difference between external and public. External means that the function can only be called from outside of the contract. Public means it can be called from another function within the contract. If you're external, you have there's an additional excuse me. you have an additional, excuse me. Sorry, you have an additional optimization as well. Excuse me. Okay, so another idea you need to think about is often people will add security into the app, the dApp. So they will have some front end that is calling their contract. And maybe they will put some security into that, which is fine in itself. But you should be aware that that is not the whole story. So your dApp that you have written will be doing an RPC call into the blockchain, which will call some function on your contract. But you should be aware that that is not the only route into your contract. Other people may also do an RPC call into your contract without going through the security that you've added to your dApp. Or other contracts may try to call functions in your contract without going through the security. Excuse me, sorry about that. Okay, so let's look at some of the best practices. So these are I've taken these from Consensus, who maintain a list of best practices for writing smart contracts. So I'll just talk through a few of these. So the first one is about using caution when making external calls. So this is the fact that you can make calls from your contract to other contracts, which is a valid thing to do, but you should be aware when you're doing this that that you need to know what code you're calling in what contract. So if there is some possibility that the contract you're calling could be chosen by someone malicious, then effectively they could be making you call some malicious code that they've written in a specially crafted smart contract. So be very careful if you're making calls to other contracts that you know what contract it is and what the effect of calling that code is going to be. And similar to that, I'm just going to skip the untrusted contract ones, but similar to that is about state changes after external calls. So as we'll see later on, the best way to do this is to, if you make an external call, or if you're going to make an external call, is to make a change to the state before you make that external call. And I'll go through why that is later. Also, you handle errors in external calls. And the pull over push idea is the idea that if you, for example, have some, excuse me, some sorry, if you have some tokens in a contract and you want people to withdraw those tokens, it is better to have a function that allows them to make a transaction themselves and go in and do a pull effectively, so go in and withdraw those tokens themselves, rather than your contract pushing out the tokens to numerous users. I'll just skip through some of these, but you can ask questions about them afterwards. Yeah, so the idea of some participants may drop offline. If you're relying on people being online for your contract to work, then just be aware that for whatever reason, participants may not be online. If you're expecting a consensus in your contract that you need people to do some vote for something to proceed, it may be the fact that people may not be online for a long period of time. So just be aware that that could happen. Negation have signed integers. So, be aware of underflows and overflows. These often cause problems in contracts where people haven't expected these. There are some language features such as assert, require and revert that allow you to check for the state in your contract, allow you to check invariants, to check that the state of your contract is what you expect, or to check that people's inputs are what you expect. So use those well in your contract. They're very useful. Use modifiers only for checks, so don't put in extra functionality in the modifier, which could have the effect of producing side effects. It makes it less readable also. So just use them to check whether a function should be called or not. Fallback functions. So these are fallback functions are special functions in a smart contract, which are called. Well, their use has changed over time. So they used to be called when Ether was sent into a contract. That has changed slightly now, but they're now called if somebody tries to call a function in your contract, but they don't have effectively the name is wrong, or how it is called is incorrect, it can end up calling the fallback function in your contract. So this is an area a way that you can do some error handling, but it has been used for exploits in the past. So it is worth making sure that these are kept simple and avoid anything that a malicious user could use to their own benefits. To answer the question about don't use transfer or send, so these used to be the main methods of sending Ether in a smart contract to some other to other users, but the reason they're discouraged in this is because the way the gas is handled in calls. So I think it's still okay to use them, but you just have to be careful about and I'd read up on this, and how the amount of gas that you will have when you've done this is going to be sufficient to what you want to do, and it may be better to use call or delegate call instead. But that's quite an advanced feature, so I think we've got a link there to the reason. Thanks for that. Okay, so yeah, those are just a few best practices. Certainly, there are other ones from Consensus. Please do read them and bear those in mind. It's really worth following those. Okay, another thing to do, I would highly recommend, and sadly I don't see this being done as much as I would like, is for people to use existing libraries. So I often see people reinventing the wheel when there are already libraries out there, particularly from the Open Zeppelin project, which do a lot of the common functions that are needed in Solidity. And because these are public and they have been well audited and they are open source, a lot of people can see them and can test them. You can be confident that they don't have vulnerabilities. So wherever you can, I really would recommend using existing libraries rather than trying to roll your own functionality and potentially introduce bugs. Just to give you an idea of what is available from Open Zeppelin, tokens, the common, the ERC20 standard tokens, and then with lots of variations on those. So doing lots of extra functionality as well as the more the vanilla ones. Also the NFTs. So for example, ERC 721s. So all of the kind of the major tokens are covered. Gas station network, that's all about helping people to, I won't go into that, helping people to pay for transactions. There is means now of extending contracts. So Open Zeppelin have a process to help people upgrade contracts. Again, this is far beyond the scope of this talk, but it's well worth looking into. And there's utilities as well, plenty of utilities that you should look at. For example, maths. If you're doing addition or subtraction, there are safe ways to do that. Check the ownership of contracts if you're trying to restrict. So rather than having to write the only owner modifier yourself, there's an open Zeppelin contract that will do that for you. So please do have a look at those and use those where you can. This will make your contracts much more secure. Once you've written your contract, I really do recommend getting someone to audit it. There are a number of companies, of course. I have to mention that we do this. So we, if you want more details of our process, please go to our security website. We also have a security newsletter there, so you can see what's been happening recently in the security area. There are other ones though, so other companies doing audits. Opens up and do a lot of audits, and they have a lot of the major projects out there will have been audited by Open Zeppelin, Trail of Bits, and also another big company. But there are other ones. So there's plenty of companies to choose from. It's worth looking at. They should be able to give you tell you what their process is and to give you examples of the audits they've done. Some companies that are being audited are happy for the audits to be published, so they may be able to point you at audits they have already performed. It's also the case, yes, if you're looking at a project in this space and you're thinking of getting involved in it, then it's worthwhile checking that it has been audited and perhaps reading the audit report. Again, if you look on our website, we have a list of major projects in the DeFi space with links to the audit reports where they have been audited, or if not, we say we show that they haven't had an audit. So I really would recommend that. It's always better to get an extra pair of eyes on the code that you've written. To help you as well when you've written your contract, I would. There are some really good tools that you can use. So so Trail of Bits do some great ones. So for example, this is one for static analysis that you can use to check over your code. Slither. Other companies, Securify in .ch, they do a website where you can post solidity code or bytecode to have it checked, and it will check against known vulnerabilities. A useful tool we've used, an inspector to help visualize flow within contracts, so it brings up this kind of thing. If you have a project that has a number of contracts with potentially fairly complex flow between the contracts, it really does help to be able to visualize it, to be able to see how it's working. And so let's look then, given this is what you're aiming for, let's look at where things have gone wrong and where we've had known vulnerabilities. There is a great registry kept that lists out known vulnerabilities in Solidity, and it keeps old vulnerabilities as well, but the most recent ones found are at the top. And this slide is not up to date. There are more there now, I think. It's great. It gives you a very good description of the vulnerability itself and gives you some test cases. So it is, before you start coding your contract, I would really recommend going through, have a look at this, read some of these vulnerabilities so that you can make sure you don't end up introducing any of these into your own contract. To give some examples now of where things have gone wrong, I mentioned the 51% attack. So this happened to Ethereum Classic. So this was just over 18 months ago, I think. This happened originally. But someone did an attack where they mined about 100 blocks, and they effectively when they dumped these onto the Ethereum Classic blockchain and did a double spend of a transaction they'd done with an exchange, and they made away with just over a million. Of course, then the Ethereum Classic, the exchanges tried to react to this, etc. I think some of this was returned, but that was done, say, about 18 months ago, and then it was done again more recently. I think in the last fortnight it's happened again. I know Ethereum Classic are working on improving their protocol to get around this. So that's an example where they returned the stuff they took. I think sometimes people do this not just for the money, but just as a technical challenge, or to show that they can do it, or perhaps to sabotage some of these chains. Certainly, if, the loss of reputation is not something to be discarded, to be thought of lightly in this. If you have a token, then and it's seen to be vulnerable, you could lose pretty much all the value in your token if it is seen, if there are vulnerabilities in your protocol. Now, before you look at this too closely, I should say that I'm not advocating in any way that anybody does this. In fact, quite the opposite. I really do not want people to do any kind of attack on any proof of work blockchain. But this is a website that is interesting, that gives you effectively the cost of performing a 51% attack against the most popular networks, and the attack is calculated from how much it would cost to set up machines in the cloud to gain enough hashing power to do a 51% attack. And as you can see, the attack for an hour is relatively high for the first few, but it becomes significantly less further down. So a lot of coins are quite vulnerable to these types of attacks. So a lot of networks are quite vulnerable. This is something that is you should very much bear in mind. But as I say, please do not take this as any recommendation to get involved with that. A different type of vulnerability at the protocol level was one that happened with ZCash, the original version, where there was effectively in an original paper that was used then to the implementation of ZCash. There was an error, and this then became implemented in the original ZCash code. Fortunately, the ZCash team, after this had gone live, the ZCash team realized that there was this vulnerability, and they managed to fix it before anybody else found it. And they brought out the second version and fixed this, and it wasn't exploited. It's very fortunate. But let's turn to some more application examples. That's really the focus of what we're looking at. So one great example, one very famous one of the first, was the DAO. A smart contract on Ethereum back in 2016. I took this screenshot when it just reached the end of its fundraising. And effectively this contract, as you can see there, owned $220 million within the contract itself. It had that much ether in the contract itself, which made it a huge honeypot. A few weeks later, it became attacked. This went out on social media. An attacker worked out how to do an attack against the DAO and to withdraw a lot of this money. There's a great cartoon about this. Here, the D symbol represents the DAO. So effectively, here is the Ethereum network giving a lot of cash to the DAO, and they burn it all, much to the amusement of Bitcoin. The exploit itself this is simplified, but this is effectively what was happening. It was really all down to the order of some statements within the contract. So at one point there was a transfer of funds, and this depended upon a balance, and this balance represented how much how much a certain account was allowed to have transferred. And this transfer was made, so the right amount was sent to the user, or in theory this is what happened. The right amount was sent, and then later on they would change the balances within the contract to show that this balance has been sent. And so they would say, okay, we've sent this amount, so this person is no longer entitled to any balances to be sent. And this was a problem because this external call happened before we changed their allowance effectively back to zero. Because what happened was someone created a malicious contract, and because in Ethereum, an address can represent either the address of a user or wallet, or it can represent a contract. So what happened was someone created a malicious contract. They represented this contract as being a user who was entitled to a withdrawal. And so when the transfer happened, this sent the ether to the contract address. So message sender here was a contract address, and it sent a certain amount that was meant to be that this contract was allowed to have. But the way the malicious contract was created was that back then, when ether was sent to a contract, it called this fallback function, and what this function did was to effectively call back into the DAO contract itself. So it set up a loop. So after line 1 was executed and it made this external call into this malicious contract, this contract then called back into before line 1, and so the whole process repeated. So it then went in and called line 1 again and resent more ether to this contract, and it carried on going around this loop. And at no point then did it actually get to the line which would zero out the amount that this contract should have been allowed to have. So the contract was effectively getting more ether than it should have. So that is why we say now, do this in another order. Don't make your external call last. So change the balance before you make the external call. And also do the pull instead of a push out to users. Another problem that was quite famous was with a multi-sig wallet that was written by Parity. It was hacked for a reason to do with ownership, and then it was then hacked again. And the way this was done was that it used a library, and there is a means within a contract to do a thing called self-destruct, and people hadn't really assumed that you would do this on a library. This was understood that you would do this on a contract, and that seemed reasonable to people, but they hadn't really thought this would be done on a library. But the multi-sig wallet was using this library, and people were using this multi-sig wallet for many projects, and the Parity team themselves were using it for their Polkadot project. And someone called this self-destruct on the library, and this caused this effectively disabled the whole multi-sig wallet. This was some tweets that the person who did this made it at the time. So DevOps 199 said what he'd done and said he accidentally killed this library. Whether this was an accident or not is open to debate. And there's even been a t-shirt printed now to say this. But it had the effect anyway of disabling this contract, and meant that the people who had funds within this wallet, they couldn't withdraw these funds. So this was a major problem. For example, with Polkadot, I think they lost effectively $90 million with this because they couldn't use this multi-sig wallet. There were questions about whether there should be a change made to the protocol to fix this, but it was decided not to do that. There wasn't really the appetite within the community to do that. Some earlier smart contract errors. Someone created a casino with a public random number generator, with a seed that was public for a random number generator, so this could be predicted what the random numbers would be. other contracts made had ether stuck because gas limits were being exceeded when they tried to do the payout. Similar to King of Ether was a similar thing. I spoke about rock, paper, scissors in the first workshop. This really happened. So somebody wrote this as a game, but it was written in a way that was cheatable, because the first person to move would always lose, because you could see what was in the transaction. Yeah. So even though those problems might seem obvious to you now, people really did write these contracts and do those. A more recent one, so this happened earlier this month. So BZX, a loan protocol, part of DeFi, they were attacked a number of times. I think initially at the beginning of the year, but then more recently as well, and they lost 8 million. Oddly, the attacker returned the funds later. I think the attacker was identified, but they, at the time anyway, got away with 8 million in various tokens that they worked out how to mint. And it was down to a bug in the contract. And it has lost, because of this, BZX has lost a lot of reputation. It has affected their price. So it does have even though the attacker returned the funds, it does have a real world effect. Okay, so before we do the Q&A, I wanted to go through, if I think we have time, some of those puzzles I sent you. Let me just go back to that. So stop sharing that one and instead share this one. Okay, hopefully you can see the gist there. If not, please say. Okay, so the first example, the idea behind this little bit of code here is that we have some kind of Oracle contract, and that is used to produce a random number, which is then used in the next bit of contract, this next lottery contract. The problem with this, I don't know if anybody spotted this, but the problem with this is that the way this random number is produced is too predictable. So you could, it's used, there's a seed used to set up the contract initially, which is used then as a modular for the block number, and that produces a random number. And this seed, all of this information is effectively public. You can get the block number, and you can also get the seed, because the transaction that was used to create this contract will be found. You will be able to find this on the blockchain and look at the parameters in that transaction and work out what the seed is. Once you've done that, then you can effectively forecast every time what this get random number function is going to produce. So definitely a very unsafe way of getting a random number. The next example is the example with, it would be a simple little app, a little contract to allow students to add themselves to some kind of list that the teacher is then going to push out some events or do something with these. The problem with this one is that we have a loop here, and this is looping through an array, but there is this array is added to effectively by anybody. Anybody can push themselves onto this array. So you could, if you were malicious, keep pushing your address or any addresses you liked onto this array, and then this loop would eventually run out of gas when it runs. So if you have a loop in your contract, do be aware that whether it's going to, whether it could run out of gas, whether what the bounds on your loop are going to be. Are they dynamic, and could they be changed by somebody in a malicious way to for example, make a loop run out of gas? Okay, the third one is perhaps more obscure. This was one that and again, all of these are real world examples. This one was one problem that I made. We had it's one of our workshops. We had a game that we were playing where we had a contract that had some vulnerabilities, and this was a vulnerability that we put in that wasn't expected. And the vulnerability itself is that this address here we've hard coded into the contract was in fact one that I'd taken from Truffle, the developer, the development environment. And so at the time when Truffle started, it would always create a set of public-private key pairs, and it would always create the same ones. And I'd used one of these to create an Ethereum address, and I thought about it and then put it into the contract. But if you ran Truffle, you would get the same address created, and so you would get the same private key. And so it was trivial for somebody in that workshop who actually just Googled this address and then found the private key and then could use that to give themselves to elevated privileges. Also, people who do this, they look through GitHub. They search GitHub for public-private key pairs as well. So be very careful that the addresses you use do not have the private key anywhere around. Let me just refresh this page because it should be, yeah, that's a fourth example. So this one was one that I heard of recently. It is perhaps a little bit more obscure, but it's an interesting one nonetheless. And yeah, it happened in a DeFi project in the last couple of months. And what somebody has done is they've assumed that this project, the contracts will be seen, and that maybe somebody will publish the contracts and the source code on Etherscan, but they've tried to disguise what the contract is doing, and to do that they've created a modifier which is called PUB1IC. So if you quickly look through this contract, you may think that there is a public keyword attached to a function, but it is not. So the function troll at the bottom there has the external keyword. So that's showing the visibility of the function. But then the word after that is not what you might think, or you might carelessly read it as being a visibility modifier, but it is actually a modifier that the person has created within their contract, and it's done there to restrict use of that to the owner. So perhaps they were trying to do this to pretend that anybody could go in and withdraw their funds. So it might look on first inspection that you could just go in and withdraw funds that you were allowed to do. But in actual fact, this would mean that only the owner could go in and withdraw funds from this contract. So someone has written something malicious in this contract to try to fool the people who may be reading this contract and thinking it's a valid contract. So do be aware of that kind of thing as well when you're looking at contracts on the blockchain. Okay, that's it. I go back to our. Let me stop the share. We'll just go back to the slides, to the Q&A. So please, if you have questions, I'm happy to answer them now. Just get the chat. I don't know if there's any that I think a lot of them were picked up. So yes, thanks for that. For those picking up. But if you have any more, yes. There you go. You should be the host now.
Thank you. Just going to allow everyone to be able to unmute themselves.
Okay, so the question pre-processing. No, I don't think there is anything like that. Obviously, you can specify the version of the compiler. Any pre-processing would be done kind of yourself, I guess. If you wanted to do some pre-processing and then have that create some solidity, then you'd have to do that yourself. Yeah.
So whoever would like to answer questions, please do unmute yourself.
Oh yes, I forgot to say while you're thinking of those, we have a security newsletter, so please go have a look at that. But also we have a capture the flag site. So we've created a game to help people with security. We have a number of levels. We're going to we add levels every so often as we find some interesting vulnerabilities. So please do go and have a play at that. It's on Rinkeby network, so you don't have to pay high gas fees or anything like that. So please do have a play with that and learn a little bit about security. Yeah.
Most of the questions, actually all the questions were answered by Brendan earlier. Yeah. But we've got a little bit of time for a couple of questions. So please do ask them while Laurence is here. Right, I guess there are no further questions, Laurence.
Okay.
Is there anything else that you would like to add?
Just thank you, everyone. Apologies for my coughing earlier on. I'm sorry about that. But yeah, thank you for attending. I hope that was useful for you. And please do be careful out there. It's a very malicious environment. So yeah, please take care of security.
Thank you very much, Laurence. That was a great workshop. And Laurence is back next week to do a workshop on CKPs. So that will be an interesting one. It's actually useful for some of the use cases that we have for the hackathon. So please do join us. We also have a technical workshop by Sol from IOV this Thursday. So please do join us for that one. Thanks again, Laurence, for your time.